In this next section, we are going to look at the definite integral. The definite integral can be broken up into three different representations, and so we're going to first talk about the numerical methods behind integration, the definite integral. The definite integral is going to be denoted very similarly to our integral or antiderivative. The main difference is now we're going to have some limits on the integral notation. Okay? This is a real number, so once we calculate it, unlike the indefinite integral or the antiderivative, we aren't just getting a function. So remember, in those cases, we're getting some f of x plus c. Here, we're actually going to come up with a number. And in some cases, that number is going to represent the area under the curve of our function over some interval. Okay? And so pictorially, if I have some function f of x that looks like this, there's a generic function, and I have some interval from a to b, then the definite integral is basically giving me the area bounded by the x-axis for the region under that curve. And the reason I say it's for specific cases is because if my function f is not entirely above the x-axis on that interval, or it has, if there's more than one function that I'm looking at, so maybe there's an f and a g, it's going to take a little bit more to figure out what the area is going to involve. Okay. So as I mentioned, we're going to look at some numeric methods. Now, before we get into this, there are many numerical methods for solving integration problems. For us, we are only going to consider one of those methods, and that's the method of Riemann sums. Okay? So for most geometric figures, so if I think circles, squares, rectangles, triangles, those nice geometric figures, we have formulas for finding the area. Okay? For curves, so generic functions f of x, we can approximate the area using these Riemann sums. Okay? And Riemann sums basically use rectangles, which we know the formula for to find the area, to approximate areas of subintervals under a curve. Okay? And to make that more clear, I have a couple examples here. We're going to take a really nice function. So obviously all of our functions are not going to be this nice, but we're going to start with these just so you can get the idea of what we're talking about. And as we move forward with these, we'll get into some of the other methods that relate to these numeric methods. Okay? So in this picture, I've got a function f of x equaling x plus 1 on an interval from 0 to 4. And for this one, I'm going to use 4 subintervals in my Riemann sum. Now, when I look at the Riemann sum, there are two ways I can approximate the Riemann sum. There's what we call left-hand Riemann sums and right-hand Riemann sums. Okay? For this one, I'm going to do both. So with 4 subintervals, I'm going to start with the left-hand side. And so I'm going to basically take my interval from 0 to 4 and break it up into 4 subintervals and look at the left-hand endpoints. Okay? So here, if I look at the left sides, or my 4 subintervals, I can basically take and divide this just on the integer values between 0 and 4. And that's going to give me my 4 regions, or 4 subintervals. Okay? And if I approximate this using left Riemann sums, I can see that my rectangles are going to take the height of the function at the left-hand endpoint. So in this case, I'm looking at 0, 1, 2, and 3 as my left-hand endpoints. And if I look at those rectangles, there's what my rectangles would look like. Okay? And so to get my area from this, it just says I'm going to use my formulas for areas of rectangles, which is basically the length times the height, or the length times the width, if you think of them kind of sideways. So for each one, I can see the length is going to be 1 unit, and the height is going to be the height of the function at that left-hand endpoint. So at 0, my function value is 1. At 1, I can see my function value is going to be 2. At 2, my function value is going to be 3. and at 3 my function value will be 4. Obviously my picture is not drawn to scale, so bear with me. Okay, and then I'm just going to add these up. But what I'm going to do before I add them is I want you to notice something, because this is going to be important when we get to our algebraic method. When we get to the end of this numeric method. One of the things to notice is if I write it out like this, the length times the height for each of these intervals, I notice that each of the lengths is exactly the same. So I can factor that out front and then just add up the heights. Okay? And so in this case, my left Riemann sum is going to have a total of 7, 8, 9, 10 times 1 or 10. That would be an approximation to my area using the left-hand endpoints of this particular interval. Okay. Now, like I said, we're going to do both left and right. So if I look at the right-hand endpoints, or the right Riemann sum, the only thing that changes is what I'm going to use as my heights. So I'm still going to have the same subintervals. Okay, I'm going to kind of draw them sideways there, on there. Okay, so the same 4 regions. The difference is now I'm looking at 1, 2, 3, and 4 as my right-hand endpoints. And so when I take my height of the function, so again, at my first one, the length is still going to be 1, but now I'm taking the height, I know that's not straight, but I'm taking the height there. So at 1, I have a height of 2. At the next one, when I come over, I'm getting a height of 3. At the next one, I have my height of 4. And at my last one, which is the value at 4, I have a height of 5. Okay. And same thing. I can factor out that length. That's the same for all of them. And then add up the heights. And so what do these numbers mean? So as I've said before, I kind of drew those lines all the way out there, but basically what we're looking at is these rectangles. Okay. So what we're looking at is the blue here is giving us an under approximation of our height, and the purplish red is giving us an over approximation of our height. And so one of the things to notice is if I increase the number of subintervals, the better the approximation is going to be. Okay? And that may not be apparent just yet, so I'm going to look at this one more time. Let's look at that same function on the same interval, but now let's look at 8 subintervals. Okay? So if I do the same thing, my left Riemann sum says I'm going to take this and I'm going to divide this into 8 subintervals. Okay, and I'm going to use the left-hand endpoints. Short. Okay, and so one of the things you can see is, well, obviously there's more rectangles that we're looking at, but if I look at the difference between the kind of open spaces between my curve and the rectangles, they're a lot less over here. Okay, and so again, in this case, I know my width of my interval for all of these is going to be 1/2. Right, so from 0 to a half to 1, 1 to a half, 3 1/2, etc. And then I just need my height of the function at each of the sub-endpoints. Okay, so again I'm starting at 0, so I'll be at 1. At a half, I'll be at 3/2. At 1, I'll be at 2. And I can keep going up until I have my 8 points. Okay, and we can see the next one would give me a value of 5, which would mean I'm at the 4, but that's the right-hand endpoint. Okay, so same thing, I'm going to go ahead and add this all up. So we'll get 3, 6, 10, plus 8, 15, 24 over 2, which looks like 12 and 10 is 22. So there's my left Riemann sum. And again, notice I didn't quite get the same thing I got here because my area is filling out more of the region. Okay. So likewise with the right Riemann sum, I'm going to see something similar, except again it's going to be an over approximation to the area. So with the right, we can see here when I do my rectangles, I'm going to get slight over approximations. Okay. And again, here where I had really big spaces between my rectangles and my curve, we can see they're a lot smaller. There's more of them, but they're smaller. Okay. So same thing. I'll take my width for all of these, which again is going to be a half. But now I'm going to use the right-hand endpoints to get the height of the function at each subinterval. And I can see that my heights here are going to start at 1/2. So I'm going to start at 3/2 for the heights. When x is a half, I get 3/2 in the function. Then at the next point, and so forth, all the way out to my last right-hand endpoint. Okay. Same thing, I'm going to go ahead and add all of these up. So we can see for the halves, I'm still going to get 24 over 2, but for these, I'm going to get 10, 14, 15, 14, 17, 18, 19. Okay, so 12 and 19 looks like a 31 over 2, which is about 15 and a half. Okay, so to continue with our numeric methods, we mentioned using the Riemann sums to find our area. And as we saw in the last example, as our n increased, so the number of subintervals increased, the approximations got a little better, meaning the rectangles got closer and closer to our curve. And so ideally, if we want to get an accurate area for this, we want our number of subintervals to be as large as possible so that the width on each of those is as small as possible. Okay? So using the Riemann sums, if the number of subintervals increases, obviously the approximation gets better. So what we want is we want our definite integral to be a sum of the heights times the widths, where we add all of those up, but we want the number of subintervals to go to infinity. And so we're going to end up taking a limit. Again, here n is the number of subintervals, delta x is the width of each subinterval, and f of x sub I is the height of the function taken in the ith subinterval. Now here there's a caveat we've got to mention, and that is, in the last example we looked at left-hand and right-hand Riemann sums. But the idea is, as I get more subintervals and my intervals get smaller, it really isn't going to make a difference what point I pick in the interval, whether it's the left hand, the right hand, some midpoint, or any other point in between. So as my n goes to infinity, Here I just need to find a point in the interval and use that to find my height. Okay. So one thing we're going to need before we can actually look at these limits is we're going to need to remember some summation formulas. So if you don't remember these, that's okay. These are the ones that we're going to use most often in these types of problems. And so the first summation formula to remember is, if I am looking at a summation, first off, I here is what we call our index. This is the variable of our summation. So anytime I see an I, I'm going to replace it with the numbers from 1 to whatever that n value is. And in this case, that n value is the letter n, or the arbitrary number n. And I'm going to sum those all up for whatever the function is. In this case, my function is k. K is just not I, so k is some constant in terms of I. And if I have a constant in terms of I, that just means I'm going to take k and I'm going to add it to itself n times. Okay? So there would be my formula. For the I, if I'm actually looking at the variable and I'm just adding that variable up, so from 1 to n, this would be like 1 plus 2 plus 3 plus 4 all the way up to n. This is just going to be n times n minus 1 all over 2. That's plus. In the case of I squared, so again thinking 1 squared plus 2 squared plus 3 squared plus 4 squared, etc. Here, this turns out to be n plus 1, 2n plus 1 all over 6. And again, if you don't remember these formulas, there are nice proofs to show that these formulas work. They require some mathematical induction. Most of you who took a pre-calc class would have seen these. If you didn't, that's okay. Like I said, you just need to know how to use these formulas. And then for I cubed, again, cubing each of my numbers from 1 to n, this is just going to be n squared, n plus 1 squared, all over 4. Okay. And then, of course, the last one that we're going to look at is if I have sums or differences of different functions in terms of my expression. These work a lot like our derivatives and integrals. I can just separate these. So I can look at the sum from 1 to n of f of I plus or minus the sum from 1 to n of g of I. And so those are the formulas we will use to evaluate our definition of our definite integral. Okay. And so another thing to keep in mind is, in order to use this definition, I need to be able to find pieces of this. So as I said, when I have a small finite number of subintervals, it's easy to find my delta x and my f of x sub I, because I can basically look at the interval and break it up easily, and then take those values and just plug them into the function. Now again, if I'm doing infinitely many of these, I don't want to write out that list. That's going to be impossible to do. And likewise, it's going to be hard to determine what the endpoints are at each one so I can get that function value. So here we want to generalize it. Okay? So an example here would be, let's just find the delta x, the x sub I, and the f of x sub I for some different functions on some intervals. And these are all going to work very similarly, and that's why I've given you two different examples here. In the first case, I'm looking at a function on an interval that starts at 0. Okay? In this case, because I'm going from 0 to 2, to find my delta x, basically I just want the length of the interval. Okay? The length of the interval is going to be 2 minus 0. And then for the subintervals, I'm just going to take that length and divide it by how many subintervals I want. In this case, there's n of them. Okay? So here, my delta x is just going to be 2 over n. Okay? For the x sub I, it means I want to take a point in each subinterval that we just found. So if my subinterval each has length 2 over n, then I can use this value to determine where the next subinterval starts. Okay? And I can just basically take and say that my x sub I is going to look like 2 over n times I. So if I is 0, then I'm at the start of my interval. Okay? If I is 2, then I'm in 4 over n, which is going to be 2 subintervals away from 0. If it's 10, I can think 20 over n, which again is going to be 10 subintervals away from 0. Okay? So if it starts at 0, it's enough to say that my x sub I is just my delta x times I. And again, my delta x here, we can think of, if this is a and b, it's b minus a over n. Okay. And then for my function, so my f of x sub I, well, I'm just going to plug 2i over n into my function. So here this is going to be 3 minus 2i over n quantity squared, or I can simplify that to 3 minus 4i squared over n squared. There's my f of x sub I. And again, all I'm doing there is I'm taking the value that I found here and plugging it into my function. Okay? So if my interval starts at 0, I can use this information here. If my interval does not start at 0, I'm still basically doing the same things. It's just that things are going to get tweaked a little bit. Okay? So if a does not equal 0, so for example, this case here, I'm looking at the interval from 1 to 4. Again, I just have some function. Doesn't matter that it's not quite the same as the one previously. My delta x, I'm going to start the same way. It's still going to be b minus a over n. So I'm going to take 4 minus 1 over n to get the length of my interval, length of my subintervals. Okay? So my delta x doesn't change any. Okay? My x sub I is going to change a little bit. Because if we think about what we said the last time, if I plug in 0, I want it to be the start of my interval. Well, in this case, if I plug in 3i over n and I plug in 0, I get 0, but that's not in my interval. So here, I have to think x sub I is going to be the start of my interval plus my delta x times I. I know I'm kind of writing off the side of the board here, so let me just move that over a little bit. X sub I is going to be the start of my interval plus my delta x times I. Okay? So in this case, start of my interval is 1, and my delta x times I is just going to be 3i over n. So again, here I can see if I put in 0 for I, then my first point is going to be the start of my interval. It's going to be at 1. If I put in 3, I can see I'm going to get 1 plus 9i over n, which is going to be 3 subintervals away from 1. Okay. My f of x sub I, same thing. I'm just going to take that and plug it into my function. So we'll get 3 times 1 plus 3i over n quantity squared plus 1 plus 3i over n for the x minus 1. And again, before I go on to use my summation formulas or write out that limit, I'm definitely going to want to simplify this. So that means multiplying out. So foiling, we'll get a 9i squared over n squared plus a 6i over n plus 1. All of that will be times 3. Notice over here the 1's will cancel. And so we'll get 27i squared over n squared plus an 18 and 3, so 21i over n plus 3. So there would be my f of x sub I. In this next example, we're going to look at using that limit definition to find the area or the value for the definite integral. Okay. So in this example, we've got the integral from 0 to 2 of x cubed minus 4x dx, and we want to use the definition to evaluate it. Okay. Again, what that means is the first thing I need to figure out is what is my delta x, what is my x sub I, and what is my f of x sub I. Okay. Okay, so this one again, if I look at my interval is from 0 to 2, which means that my delta x is going to be 2 minus 0 all over n, or 2 over n. Okay. My x sub I, again, because my interval is starting at 0, I know this is going to be 2i over n. And so to get my f of x sub I, again, I'm just going to take this and plug it into my function to get the function value within each subinterval. So we'll take 2i over n and cube it minus 4 times 2i over n. And again, I can simplify this, and we can see that I'm going to get an 8i cubed over n cubed minus an 8i over n. Okay. So here, my integral from 0 to 2 of x cubed minus 4x dx is going to look like the limit as n goes to infinity, my sum, I equal 1 to n, of my function times my delta x. Okay. Now, a lot of this problem is algebraic, so I'm going to just need to simplify this algebraically, take my summation, and then take my limit. Okay, so first thing I'm going to do is just multiply my f by my delta x. So we'll get a 16i cubed over n to the 4th minus a 16i over n squared. And then I'm going to use my summation properties to rewrite. Okay, so remember, for the summation properties, it says if I've got a sum or a difference, I can break those apart. Okay, so this is going to be the sum, I equal 1 to n, 16i cubed over n cubed to the 4th, minus the summation I equal 1 to n, 16i over n squared. Okay. Now 16 and n to the 4th, those are pretty much coefficients in terms of my functions in terms of I. So those can be moved out front just like all of our other properties that we have. So I can say this is 16 over n to the 4th times my summation for I cubed. Likewise over here, the 16 over n squared can be brought out, and then I can just look at my summation for I. At this point, this is where I'm going to use my summation formulas to get everything in terms of n. So here, my limit as n goes to infinity, I'm going to drop the summations and rewrite them in terms of their expressions. So the 16 over n to the 4th gets carried along. The summation of I cubed, we said, is n squared n plus 1 squared over 4. And then the 16 over n squared is going to be multiplied by our summation for I, which was n plus 1 over 2. Again, probably want to simplify before I try to take my limit. here I can see n squared times n plus 1 squared. When I go ahead and multiply that out, we'll get a 16 n to the 4th plus a 32 n cubed plus a 16 n squared all over 4n to the 4th. Same thing over here. When I multiply out, we'll get a 16n squared plus the 16n all over 2n squared. Again, to take my limit, well, these are nice rational functions. Nice thing about rational functions, if I'm taking the limit as it goes to infinity, is I only have to consider the dominant terms. So for this first one, my dominant term is 16n to the 4th over 4n to the 4th. And likewise over here, my dominant terms are 16n squared over 2n squared. The other terms are negligible as n goes to infinity because these are going to tell me where it's going to go. And notice in these cases, I can cancel out the n's. So I'm looking at the limit as n goes to infinity, 16 over 4, which is 4, minus 16 over 2, which is 8, says the limit as n goes to infinity of negative 4. And if I look at that, well, there's no n's left, so that tells me my value is negative 4. So there's the value of my integral over that particular interval from 0 to 2. Okay. Again, this was a nice example because in this example, I'm starting with an interval that begins at 0. And so finding my delta x and my x sub i's are fairly straightforward. In this next example, we're going to look at the same type of thing. We're going to evaluate a definite integral, but this time it's not going to start at 0. So here we're looking at one that starts somewhere else. Whether it's a positive number, a negative number, doesn't matter. Just something that doesn't start at 0. Okay? So in this case, again, we're going to start by finding our delta x, which again is basically the length of the interval divided by the number of subintervals. So here, our length of our interval is going to be 3 minus 1. Number of subintervals, again, is just n. So 2 over n will be our delta x. For the x sub I, again, in this case, we're going to look at delta x times I, but we have to consider the start of the interval. So in this case, it starts at 1 plus our delta x times I. Okay. To get our function value, we're again just going to take this and plug it back into our f of x. So here we can see we'll get a 1 plus 2i over n quantity squared, 3 times 1 plus 2i over n plus 4. Again, probably want to simplify this before I try putting it into my limit. So we'll get a 1 plus a 4i over n plus 4i squared over n squared. So foiling that out, plus 3 plus 6i over n plus 4. Combining terms, says our f of x sub I will be 4i squared over n squared plus 10i over n plus 8. Okay. So our integral from 1 to 3 of x squared plus 3x plus 4 is going to look like the limit as n goes to infinity of our sum, I equal 1 to n, of our function times our delta x. Okay, again, we want to start by simplifying that. So we're going to go ahead and distribute that 2 over n. So we'll get an 8i squared over n cubed plus 20i over n squared plus the 16 over n. Now again, we can separate. So we'll separate these out into 3 separate summations. Pull our coefficients out front. So we'll get an 8 over n cubed times our summation for I squared plus a 20 over n squared times our summation for I plus the 16 times our summation, that's backwards, 1 over n times our summation for 16. So there's our constant. Okay. Again, for these 3 summations, we can now use our formula. So we have the I squared formula, the I, and the constant formula. So here we'll get 8 over n cubed multiplied by our summation for I squared, which is n plus 1 times 2n plus 1 all over 6. Oops, it's a plus. 20 over n squared times our summation for I and our 1 over n times our summation for 16. Okay. Just like the last one, we want to clean this up some so that we can take our limit. So here again, I want to multiply things out. So multiplying out here and then multiplying by 8, I'm going to get a 16n cubed plus we'll get a 24n squared plus an 8n all over a 6n cubed. For the middle terms, we'll get a 20n squared plus 20n all over 2n squared. And for that last term, 16n over n. Okay. Again, we can look at this as a limit of some rational expressions. So we are going to pull off the dominant terms. So our dominant terms here are the 16n cubed over 6n cubed. Here it's the 20n squared over 2n squared, and, well, 16n over n. Again, like the last one, I can see that things will cancel out. So limit as n goes to infinity, we're looking at a 16 over 6 or 8/3. 20 over 2 or 10, and 16, which we can simplify. It's going to be a 26 which we can take the limit of a constant, is just that constant, and we can see when we multiply we'll get an 18, get that wrong, we'll get 26 times 3, which is 18, and 1, 78 plus an 8, so it'll be 86 over 3. A couple of things to keep in mind when you're doing these. So again, the first is you have to be careful on your x sub I, and it'll depend on whether or not your interval starts at 0 or some other number. Once you've simplified and gotten your function, remember your summation formulas, and there again it's just knowing which ones of those to use. On an exam, I will give you the summation formulas, you just need to know how to apply them. Okay? The other thing to keep in mind is once I get down to this limit stage, and I'm actually starting to take the limit, notice in every one of our examples, we no longer have ends after this point. Okay? If you are getting ends that are not canceling out, that means you made a mistake in your algebra somewhere. Okay? At this point, once I cancel out and I'm looking at the dominant terms, everything should be a number. Okay? And these will always work out to be some number, as we've said before, for the definite integral. Okay? On an exam, you're going to be expected to do at least one of these. This will show up on the final as well. And again, the way you're going to know to use this method, as opposed to some of the other methods that we're going to use, is that it's going to say use the definition. So it's going to have that definite integral in there, meaning there's limits on it, but it's going to tell you specifically to use the definition.